Hello everyone. Welcome to this new lecture. Let us just get started right away. I want to wrap up this topic of index modulation that we had started out with, and then maybe come back to this beamforming topic that we were on. So let us see how much progress we can make today. By the way, I hope you all are able to hear me and see my screen, etc. If not, just let me know, and we'll work out something.
Yes, sir.
Okay, good. So essentially, this scheme of spatial modulation that we were discussing last time, it can be thought of as actually having multiple antennas at the transmitter create multiple dimensions. But these multiple dimensions are created in the space, actually. It is, they are created because of this fading channels. They are not arising because we are asking for more bandwidth, which is what we would have to do if we didn't have multiple antennas. I think we saw last time that in case of single antenna, the only way that you can create additional dimensions is by requiring more bandwidth. And when you require more bandwidth, your spectral efficiency goes down. And the promise of MIMO, and in specific this spatial modulation, is that that is not happening. We are able to somehow magically get more data rate, higher bits per second, without requiring a corresponding increase or even a greater increase in the bandwidth. We saw that the spatial modulation can be thought of as having two perpendicular dimensions. And so let me try something new here. This is the first time that I'm doing it. Let's see if it works out or not. Okay, so this is my one dimension, and then this is my other dimension. And then on one dimension, which is antenna 2, I'm going to activate some 4 symbols like this. Let's say these are QPSK symbols. And then on the other dimension, which is antenna 1, I will, so this is antenna 2 actually. So I'm going to activate 4 symbols like this. So this is antenna 1. And this is over here is antenna 2. And so you see that when I'm, for example, activating this symbol over here, I don't need to activate antenna 2. These 4 QPSK symbols that I'm schematically showing along this horizontal dimension are being activated only on antenna 1, are being transmitted only using antenna 1. Whereas when I use antenna 2 to transmit this particular symbol, actually the same symbol of QPSK, I don't need to activate antenna 1. So I have 2 transmit antennas. At a time on individual transmit antennas, I am actually doing the same QPSK transmission that I would do in a normal case when I have only single input, single output configuration. So it appears that how are things any different? Because we are activating only one antenna at a time. On that antenna, we are transmitting as if it is the same traditional QPSK transmission. So what are we doing new? Well, this diagram here shows what we are doing new. We are actually able to have 8 different constellation points. instead of 4. And the reason why we are having this 8 different points is because somehow we are able to make antenna 2 to be in a perpendicular dimension compared to antenna 1. And so at a time, we are selecting 1 out of 8 possibilities, which means that even with QPSK, which otherwise gives us only 2 bits per second, here we are now getting 3 bits per second. And that additional extra bit came because the receiver independently figured out whether the symbol transmission happened over this vertical dimension or over this horizontal dimension. See, if the receiver somehow had no capability to figure out that this QPSK symbol is different from this QPSK symbol, then this whole scheme will come crashing down. We won't be able to support this 1 extra bits per second every time we transmit a symbol. Because remember, this symbol and this symbol are identical QPSK symbols. They are exactly the same symbol. Over here, we are transmitting the same 4 symbols that we are transmitting over here. Typically, we are used to seeing QPSK symbol in a rectangular manner. For the sake of simplicity in visual representation, I am stacking them in a vertical manner. But that should not confuse you. These 4 symbols are the same QPSK symbols that we have seen earlier. It's just that I'm visually showing them in this particular manner. And so somehow we are relying on the receiver to figure out that when it receives the exact same QPSK symbol, this symbol is somehow different from this symbol. And that difference is coming only because it has been transmitted now on a different antenna. So that is the main underlying novelty of the spatial modulation. And we have seen that the space shift keying is even simpler version of spatial modulation, where we just activate one antenna at a time, and we ask the receiver to figure out autonomously, independently, which antenna was activated, and that allows the transmitter to send information to the receiver. Actually, no traditional manner of symbol transmission is happening, and it is therefore called space shift keying. Actually, it should be called antenna shift keying, maybe alternatively. But anyhow, this is the name that is used in the literature. Okay, so, by the way, we saw last time that this concept of space shift keying is actually completely analogous to that orthogonal frequency modulation concept that we have seen in the earlier course. The only difference is that these orthogonal dimensions are now happening by means of multiple transmit antennas instead of requiring multiple frequencies. Okay, so let us now look at this in a little more maybe organized manner. So we will start with the simpler scheme, which is the space shift keying, and we will see what the transmitter is doing. As we have said, the transmitter will have a total of some NT antennas, and it will just send a continuous wave signal on each of these antennas. Essentially, it will activate that antenna. If you think of the RF radiation that is coming out of this transmitter as just part of electromagnetic spectrum, if it was visible spectrum, it would be as if we are just turning on the switch of a light bulb. And then that light bulb just emits some constant frequency radiation. And so this would be the diagram of this space shift keying. It has a total of log base 2 of NT bits that is incoming. And using that sequence of bits, only one of these NT antennas gets activated. So for example, if we have 4 antennas, then this will be sort of like any 4-array modulation scheme. You will take 2 bits at a time. If it is 0, 0, you will activate first antenna. If it is 0, 1, you will activate second antenna. And if it is 1, 1, then you will activate the fourth antenna. Okay, so that is the simplicity of the scheme here. Very, very simple scheme. And you will see now that every time that I made use of channel, I am able to transmit 2 bits. So the net information transfer that I am able to accomplish is 2 bits per channel use. It is sometimes called BPCU. This concept, this nomenclature of BPCU is actually, in fact, we can prove it. And this is what I will ask you to do offline. This BPCU is same as bits per second per hertz. It's an alternate way of writing spectral efficiency unit. So take a moment later on after the session is over and see why this notion of bits per channel use is equivalent mathematically to bits per second per hertz. Obviously, then you will see that the numerator is the same, it's bits, whereas in BPCU, the numerator is channel use, whereas in bits per second per hertz, the numerator is second per hertz. So how come second per hertz and channel use are the same? That is the question that you should ask yourself. But for the time being, let us take this as the measurement of spectral efficiency. Okay, so you will see that the spectral efficiency is dictated by how many antennas I can have at the transmitter. Now, what about the receiver? What does the receiver do? First of all, we will require the receiver to have an array of antennas also. It will be difficult, if not impossible, for the receiver to detect which antenna was selected by the transmitter if it had only one antenna, if this NR was 1. Typically, we want NR to be at least 4, or maybe more than 4 is better. So this is the diagram of the receiver. It has a total of NR antennas, and this is the channel between the transmitter and the receiver. And we will call H of J to be this NR cross 1 vector from jth transmit antenna to the receiver antenna array. Now, one key requirement of this phase shift keying or SM is that the receiver knows all of the channel vectors. So there are a total of NT different channel vectors, H1, H2, up to H of NT. Each of these channel vectors is an NR cross 1 vector. And so we are requiring that the receiver has knowledge of all of those channel vectors. And so now what the receiver does is it takes that antenna as the one most likely to have been transmitted, for which the measurement that it obtains, this vector y, and this channel vector h of j, the difference between them in the squared norm sense is the smallest. Okay, so what is this methodology? Can you tell me? This detection scheme, which which selects the antenna for which this squared norm becomes the smallest. What have we called it earlier?
Least square.
No. When we
Euclidean distance.
Yeah, so it is. This is Euclidean distance, and we are minimizing the Euclidean distance. So this is called the minimum distance detector, right? We have studied this, I think, earlier in the earlier semester. So this is the minimum Euclidean distance detector scheme. Now, if I assume that the only difference between h of j and y is, when the transmitter has selected jth transmit antenna, the only difference between y and h of j is the white Gaussian noise, the vector of noise samples. Then this minimum Euclidean distance detection scheme becomes identical to what? Assuming this Gaussian assumption. So with Gaussianity, what does this scheme amount to? What are the detection schemes that we have studied in CT516? One was this minimum Euclidean distance detection.
MAP.
Right. We studied map scheme, and then there was the other scheme was correlation receiver, but there was one simplification of map that we made.
Maximum likelihood.
Right. We studied maximum likelihood detection, and the maximum likelihood detection is different from the map only in that. What is the difference between ML and map?
The A posterior is provided beforehand in MAP. In case of ML, it is not.
In case of ML, it is not. But then, what is the assumption for ML then?
The probability of all these symbols is 1.
Yeah, probability of transmission of each of these symbols. It's not 1; it is 1 over n of t. Basically, the likelihood of each antenna getting selected is equal. So if it was 4 antennas, then we assume that each antenna gets selected with a probability of 1 over 4. In the maximum a posteriori scheme, the prior probabilities are different. Maybe antenna 1 will get selected 80% of the time, and antenna 2 will get selected 10% of the time, and then 3 and 4 will get selected 5% of the times. So those prior probabilities are not equal in the map. The only difference between map and ML is that those prior probabilities are equal, and so we can ignore them in our derivations. And then what happens is when we maximize the posterior in presence of Gaussian noise, the conditional PDF has an exponent which is essentially this squared norm, except there is a negative sign in front of it. And so that maximum likelihood metric, we simplified it by taking logarithm first and then removing the minus sign. And so if we are trying to maximize the posterior probability, once we remove this minus sign, we have to minimize this squared norm. So that is how we showed in CT516 that this is same as the maximum likelihood detection. So this is the main idea behind how the receiver is going to determine which of the anti-antennas has been selected. It is essentially going to perform the maximum likelihood detection, assuming that all the antennas are equally likely to have been selected. Now, I think someone mentioned that it can be also thought of as, this scheme can be thought of as correlation detector, which is actually a simplified version of doing the norm calculation. And so that is what we will look at now. So let us write down the model of the received signal. Y is equal to capital H, where H is NR cross NT MIMO channel matrix. This matrix is fundamentally no different from that capital G matrix that we had seen in the previous lecture. The different columns of those G matrix, of that G matrix were our different basis functions. Likewise, here different columns of H matrix are our new basis functions that are getting generated purely through this MIMO architecture. Now remember, we have said that a space shift keying is analogous to the orthogonal modulation scheme, where we select only one dimension at a time. So maybe we'll just go back to that. So remember last time we said that in the orthogonal modulation scheme, one of the dimensions is selected. All the other dimensions, when I select this particular symbol, it means that I am not putting out energy on any of the other dimensions. And so that is where in the equivalent sense for the space shift keying, I can say that I'm transmitting actually this vector 1, which is essentially all zeros, except the antenna which is selected or the dimension which has been selected will have 1 corresponding to it. And then n is the vector of additive noise that the receiver error sees. Okay, so this is how visually the transmission pattern looks like. This is a vector of 1s. It is actually NT cross 1 vector. And at a time, I am activating only one of these elements. All the others are zeros. And then this is the channel matrix, and this is the received vector corresponding to the channel matrix. Essentially, because of this particular formulation of the one vector, this matrix here that I'm showing will essentially be just one of the columns of H. It will be, in this case, it will be which column of H? Third column of H. Right? If I had selected this to be the non-zero element, then at the receiver, in absence of noise, I will see the last column of H, and so on. Okay. So we have seen that minimum Euclidean distance detection scheme can also be implemented by using correlation method. And again, I think you can revisit the class notes of CT516 to see how the equivalence comes about. But for the SSK, this correlation-based scheme is equivalent to the maximum likelihood scheme. And so in correlation-based scheme, all that we do is we multiply Y with Hermitian transpose of H. Remember, we have said that the receiver is assumed to know channel matrix H. And so now, if I expand out the expression of Y, then this is the expression that I get. If I further assume that these columns of H are orthonormal, which is maybe if NR is large, if NR is, for example, 64, or maybe even 32 is pretty good, then I think in some of our studies we have seen that this orthonormality assumption is more or less accurate. But if NR is small, then H Hermitian H doesn't become identity matrix. But if you assume that somehow I'm able to make this H matrix to be orthonormal, then H Hermitian H becomes identity matrix of size n of t. Remember, H is nr cross nt, so when I do H Hermitian, it becomes nt cross nr. And so now nt cross nr times nr cross nt will give me identity matrix of size nt. Then you will see that my estimated one vector is actually the original one vector plus the additive noise after it is transformed by H Hermitian matrix. And so now all that I want to do is select that particular element of this one hat, which I have formed using this simple scheme, for which the real part of that vector is the highest, because all the other values will be very small, assuming that the noise power is small compared to this transmission power. Okay, so this is in a nutshell how the receiver will determine which antenna has been activated. And that essentially completes the description of the space shift gain. There is all there is to it. Okay, the SSK is completely, the concept of SSK is completely captured here in these two slides. And in fact, if the earlier descriptions that we have studied of the maximum likelihood detector, maximum a posteriori detector, etc., and eventually we went on to look at the correlation detector. I suggest that you open up those class material of CT516 and correlate, or rather compare these two slides with the material that we had studied as part of CT516. And that will allow you to observe that this here, this scheme that we are describing here, is actually no different from what we would do if it was an orthogonal modulation scheme. In the orthogonal modulation scheme, this is exactly what we would be doing. The difference between the orthogonal modulation scheme that we have studied in CT516 and SSK is that this H Hermitian H is not guaranteed to be the identity matrix, because it depends on what the actual channel variables are. And so that is the main difference. Now, Divya pointed out exactly the same question that I was going to ask you, whether this diagram reminds you of anything that we have done earlier in this course. And I think Divya already kind of answered that question, that you see this diagram allows you to observe that this vector of ones, this one bar that I have mentioned here, is highly sparse. There is only one element which is 1, all the others are zeros. And typically we can say that we want to use as small value of NR as possible. We want NT to be as large as possible, because only when we make NT large enough, then log base 2 of NT will be large, and so we'll be able to transmit more number of bits. But we don't want NR to be very large, because simply because it requires us to have a receiver which is more complex, which is probably more costly. If you're talking about handheld devices, then forget about making NR to be 16. It will be very difficult to have 16 antennas on your phone. So yes, we can make, for example, NT to be 16. Maybe we can put 16 antennas on the top of a tower, but let's not ask for so many antennas at the user device. And so when NR is small, NT is large, this H matrix becomes like a flat matrix. And so what we have here is actually an underdetermined system of equations. But that is what we have already seen in the context of expectation maximization algorithm. It is actually leading us to the compressive sensing based schematic. So we can actually apply compressive sensing algorithms also to discover which antenna has been activated. So you see that compressive sensing brings up its head in this new topic, which is kind of not on the face of it. It has nothing to do with that sparse Bayesian learning based direction of arrival estimation that we were considering. Now, in that context, I don't have a separate slide for it, but let me ask you this question, that I extend this concept of compressive sensing and say that why do I need to restrict only to activating one antenna at a time? Why do I need to have only one non-zero element? Maybe I will have two non-zero elements, right? And let us say that I have 5 antennas. In this SSK scheme that we are looking at, I'm activating 1 out of 5 antennas at a time. And so how many, what type of BPCU number will I get? When NT is 5, the SSK will give me 5 bits per second? No? First of all, remember, we are not talking about bits per second here. We are talking about bits per channel use. Every time I make use of channel, how many bits I am able to transmit when I have 5 antennas? We went over this here, right here.
Log to the base 2 of 5.
Log 2 of base, yeah, log of 5 base 2. Yes, Arushi is also right. Now, obviously, that is a non-integer number, so we will not be able to make use of the 5th antenna. Typically, we want NT to be a power of 2. And so that is how we get 2 bits per channel use. Okay, so the answer is that with 5 antennas, I am able to transmit 2 bits every time I use the channel, which is same as not 2 bits per second, but it is same or equivalent to 2 bits per second per hertz. And in that case here, I have one entry which is non-zero at any given time, and the other 5 entries of this column vector are going to be zeros. Now, if I extend this and say that, well, I will deploy some compressive sensing algorithm and figure out not only which one antenna was transmitted, but at the receiver using the CS algorithm, I can even figure out which 2 out of 5 antennas have been selected. And so at the transmitter, I will activate not only one antenna at any given time, but I will activate some random selection of 2 antennas out of 5. Essentially, there will be 2 non-zeros in this vector, and the rest will be zeros. And that starts becoming a lot like compressive sensing. This vector still is highly sparse. It still is mostly filled with zeros, but we are not handicapping ourselves by saying that there will be definitely only one non-zero at any time. All the other anti-minus elements of this vector will be zero. We are saying that we are being a little more ambitious. We want to activate 2 antennas at a time. Now, the question to you is, in that case, what will be the bits per channel use? How many bits will I be able to transmit if I am willing to activate 2 antennas whenever I make use of channel? And assuming that using this compressive sensing framework, or maybe even using this variant of maximum likelihood or minimum distance detection, the receiver is able to figure out which of the 2 antennas have been selected by the transmitter. So that is the question to you. Okay, so think about it, and I'll be back in just a moment. Okay, so back. Any thought on the question that I had asked? Okay, so let us see who all are here. Okay, Anudeep, did you get my question? Anudeep, are you there? Okay, Anudeep is there. Then did you understand the question, Anudeep? Yes, no? Okay, so Anudeep understood the question, but maybe he's not having the answer with him. Arushi, what about you? Arushi, are you there?
Hello. Yes, sir. Sir, can you please just repeat the question again? Because
Repeat the question.
yes, sir.
Okay, who can repeat the question to Arushi? Divya, can you ask the question to Arushi?
Yes, sir. So sir is asking if we activate two antennas instead of one, then what will be the bits per channel used?
Yeah, we already saw that with one antenna, I am able to transmit log base 205 bits per channel use, which amounts to essentially 2 bits per channel use. So if I activate 2 instead of 1 out of 5, okay, so Arushi, I will let you think about it. Who else? Komal?
Yes.
Yeah, do you have the answer?
I don't know it is correct or not, but I just thought it will be summation of two times summation of log 5 base 2.
2 times log 5 base 2, okay? Yeah, okay, fine. I think you are kind of thinking along the right direction. But the answer is actually not that. So let me see. Is Bibin here?
Yes.
Okay, Bibin, maybe you can take it up. You can tell them.
Uh, okay, so we are activating two antennas out of five. So what we have to think like what all are the possible two antennas that you are going to activate. You can activate antenna number 1 and antenna number 2, or you can activate antenna number 1 and 3, 1 and 4, 1 and 5. So you got four possible combinations, and another combination is 2 and 3, 2 and 4, 2 and 5, and so on. So the total number will be 5 choose 2, and floor of that floor log to the base 2, 5 choose 2.
Right. So remember from CT516, I think earlier on we said that what matters is the ability of the transmitter to make selections. If the set over which the transmitter is able to select is larger, then the transmitter is able to transmit more information. I think we did this at one of the early first few lectures of CT516. And we actually that time said that it doesn't matter what that set is. The actual members of that set is not critical for engineering problem. It is actually the size of the set which is more relevant. So if suppose our English alphabet was only 4 letters, A, B, C, D, then we would be able to transmit only 2 bits every time we make use of one of the 4 letters. But we have 26 letters, and so we are able to transmit maybe not as much as 5 bits, but 5 bits of information, but maybe slightly more than 4 bits of information every time we select one letter. When we make when we transmit QPSK or iterary PSK, the difference is that in QPSK our transmitter has a set which has 4 members. In 8PSK, the transmission set has 8 members. And so that is why 8PSK allows us to transmit 1 extra bit of information every time we transmit one of the 8 symbols of 8PSK compared to one of 4 symbols of QPSK. Again, the actual form that the symbol takes doesn't matter. In the space shift keying, our symbol is actually an antenna, in fact. It doesn't look like a QPSK symbol or a letter of alphabet or anything. So now we have something which is our symbol. Our symbols don't look at all like what we are used to. They don't look like our conventional QPSK, PSK form type of symbols. They don't look like the symbols of our language. But nonetheless, in the idea behind the space shift keying is that we are giving the transmitter an ability to choose one member out of a set. In the conventional SSK, that set is having a total of NT different elements. What are those elements? Those elements are nothing but the indices of these NT antennas. Right, so our symbol transmission set has total of NT different symbols. These symbols are actual physical antennas. Okay, so they don't look like symbols, but effectively the transmitter has ability to select one of NT different entities, NT different components, or NT different members of this set. So in that sense, the space shift keying and the SM actually abstract out the idea of how we are able to transmit information. All that the transmitter needs is a set with some number of set members, and it needs complete freedom in terms of selecting one out of those set members. And then it needs an assurance from the receiver that the receiver more or less will be able to figure out which symbol was selected by the transmitter. So in this scheme that we were looking at, if here this vector 1 had 2 non-zero elements, like what Bibin pointed out, our set will become larger. It will have total of 10 members. What are those 10 members? The way Bibin described, antenna 1 and antenna 2, antenna 1, antenna 3, and so on. So there'll be total of 10 pairwise choices that now the transmitter is able to make. And so the number of bits that it will be able to transmit is now 3 instead of 2, because log of 10 base 2 is at least 3, more than 3. So at the expense of making the task of the receiver a little more difficult, I am able to transmit 1 more bit per channel use. And I don't have to stop at activating only 2 out of 5. I can activate 3 out of 5. And then I will have even more number of elements in my set that I'm selecting from. And so I'll be able to transmit even more number of bits. So you see that it affords us kind of a capability to trade the receiver complexity against the bits per channel use that we are planning to transmit. Obviously, we don't want to take it too much ahead, because in the other extreme case, instead of activating one antenna, if I allow freedom to activate all NT antennas, then actually I'm back to this spatial multiplexing MIMO that we had seen last time. This is the full-fledged MIMO, where all the antennas are on all the time. But when I do that, I run into these problems of ICI, IAS, and RF chains. So essentially, the phase shift keying is a compromise. This architecture that I'm showing here is the extreme compromise, where in order to avoid the various problems of this S-MUX MIMO, I simplify to the maximum and say that I will transmit only one antenna. I will activate only one antenna. But obviously, at the expense of little more increased complexity, I can possibly activate two antennas out of NT, and that thereby I can further try to improve on the bits per channel use. If I try to do that, then the right answer is to not necessarily go through this math, but instead of that, do one of the compressive sensing algorithms that I think some of you have been looking at. Okay, so that is the phase shift keying. The spatial modulation is actually very much like phase shift keying. In fact, the upper part of the transmitter looks exactly like phase shift keying. But in addition, on the selected antenna, instead of just transmitting continuous wave, single frequency sinusoid, the spatial modulation additionally puts M-array symbol. And so now I'm able to transmit log base 2 NT plus log base 2 M bits per channel use. If NT is 1, which is the conventional case, then this term goes away, and then log base 2 M is the same conventional modulation scheme, the spectral efficiency of the conventional modulation scheme. If capital M is 1, then this log base 2M goes away and I get back to SSK. But otherwise, I have both of these terms present. At the receiver now, what I will have to do is, I will have to not only detect which of the antennas has been selected, but then also detect which symbol has been selected out of the total of M possibilities. And so the SM has a slightly more complicated receiver. One way is that it will first detect the antenna and then it will select the transmitted modulated symbol. But this is not the only way that the receiver can operate. In fact, it can actually say that my transmitter is going to transmit total of some 8 symbols. And I don't care that these 8 symbols are coming from 2 different antennas. All that I care is that there are going to be 8 symbols. And then I will figure out which of these 8 symbols was transmitted just as if it was an 8-array PSK transmission or 8-array QAM transmission. And so I will use exactly the same mathematics, either maximum likelihood or minimum distance detection, to determine which of these 8 symbols has been transmitted in this SM. Then once I do that, I will, as a byproduct of that detection scheme, I will know which antenna was activated. But that really is not my objective. My objective is to just get these 3 bits that were transmitted. So then there will be no such clear demarcation between first detecting the antenna and then detecting the modulation. These 2 blocks will be kind of merged together. Okay, so let us conclude this by just taking a quick example of this spatial modulation scheme. So here in this scheme, I have assumed that there are 4 antennas, and after the transmitter selects one of the 4, it sends a BPSK symbol on that selected antenna. So if you look at any particular instant of time, it will be just like a conventional BPSK transmission, because only one antenna has been selected. And so on that antenna, you will see that either 0 or 1 is transmitted. So the last column here is just 0 and 1, 0 and 1, 0 and 1. But remember, now I have 4 antennas, and so on each antenna, I am able to transmit either 0 and 1. If I transmit BPSK symbol on the first antenna, then the corresponding bits become either 000 or 001. Whereas if I have selected the 4th antenna, then effectively I am transmitting either 110 or 111. Alternatively, with 4 antennas and 2 symbols, I have a total of 8 constellation points. And I am selecting one of those 8 constellation points using 3 bits. Does this table make sense? Okay, who all are here? Joel, are you here? Yeah, okay, I don't see Joel. Nidhi, does this table make sense?
Yes, sir.
Okay. So it's just a tabular way of describing the concept of space modulation. What does this table tell us? Yeah, okay, so I think this one actually is a diagram that came from some of the work that Bibin has done earlier. So what this is showing is, as a function of time, how the transmission pattern will look like. So now x-axis is the time axis, and let us say that incoming bits are 110. So I'm going to select the 7th symbol. For the 7th SM symbol, the BPSK symbol is S1 and the antenna is A4. So at the very first symbol interval, I will see that 4th antenna is activated, and on that I have transmitted BPSK symbol bit 0. Then if 011 is the next 3 bits, then I will activate 2nd antenna, and on that I will transmit BPSK symbol 1, and so on. So this is how my transmission pattern will look like. If I look at any column, then you will see that it will have only one non-zero element. The other 3s will be zeros, because only one out of the 4 antenna has been selected. So now I am able to achieve total bits per channel use of 2 plus 1, total of 3 bits. Okay, this is some detailed version. Maybe we shouldn't spend too much time on it, but the original paper that described this space modulation, it said that what if I have an OFDM system, then actually I can do this transmission on each OFDM subcarrier. So on subcarrier 1, I will be transmitting in this manner. Then on subcarrier 2, I will be using some other sequence of 3 bits, and I'll be transmitting symbols like that, and so on. So basically, I will have multiple such subcarrier transmissions going on in an OFDM system. The effect is that now if I look at any particular antenna on a particular subcarrier, there will be only one active antenna. The other 3 antennas will be non-active. But if I look at all the subcarriers, then it is quite likely that all the 4 antennas are active. Maybe antenna 4 is transmitting on subcarrier 1. Antenna 3 might be transmitting on subcarrier 2, and so on. It could also be that antenna 4 is transmitting S1 on subcarrier 1 and maybe S2 on subcarrier 2. There can be all sorts of possibilities. But now, in general, at any given time, all the 4 antennas may be active. So one of the advantages of SM that we need less number of RF chain is not present here. But on the other hand, we are able to get many bits per channel use because we are, in this example, we are putting 3 bits on each subcarrier. And so now if I have a total of capital N subcarriers, then the total number of bits will become 3 times capital N. So this is just one example of space modulation with OFDM. Here I have merged the concept of space modulation and OFDM together. Maybe one question I will ask you is, when I do that, am I able to improve spectral efficiency in terms of bits per second per hertz? What is the spectral efficiency of this scheme in bits per second per hertz? Okay, who is in the line now? Soumya, do you know?
No, sir.
Kishan?
Sir, we have to multiply with small n, like if there are like capital N subcarriers, and each subcarrier having a BPC of log 2 nt plus log 2 m.
Yeah, I mean, this example, let's just take that each subcarrier is able to transmit 3 bits. So by doing OFDM transmission over n subcarriers, am I able to improve spectral efficiency?
I think so, yes, sir.
Okay. So, okay, Divya, what do you think? And my spectral efficiency is increasing?
Yes, it is.
Okay, spectral efficiency is number of bits per second divided by the bandwidth. So number of bits that I'm able to transmit, yes, is getting multiplied by n. Instead of 3 bits, I'm transmitting now 3 times n bits. Because on each subcarrier, I'm transmitting 3 bits. So the numerator is definitely getting multiplied by this capital N. But what is happening to the bandwidth now? Compared to the bandwidth of one subcarrier, this capital N subcarriers will collectively occupy n times larger bandwidth. Right? So the ratio doesn't change. So it will not be correct to say that my spectral efficiency is increasing. On a per unit of spectrum, I'm still transmitting 3 bits. But what this scheme allows me to do is, if I have more bandwidth, then I can put more and more number of subcarriers, and effectively I will get higher data rate. Does that make sense?
So that will still be at the cost of bandwidth only, no? I mean, increased bandwidth for increased data transmission.
Right. So no change in bits per second per hertz, because number of bits goes up, but the hertz also goes up in the same proportion.
But sir, in OFDM, the bandwidth is divided into small units so that we use it on like different subcarriers, right? The same bandwidth we divided into multiple subcarriers. So how it is increasing?
So let us say we have the 4G LTE system. So subcarriers take 15 kilohertz in LTE 4G. If I do this space modulation on the single carrier, let's say I say that I don't want to transmit all the subcarriers of OFDM, I will just transmit my information only on one subcarrier. Then I'm transmitting 3 bits over 15 kilohertz.
Okay, that way.
But if I employ capital N subcarriers, all of them, then
N into 15.
Then the bandwidth becomes N times 15 kilohertz. So the denominator goes up. Numerator becomes 3 times N, but the denominator becomes 3 times 15, and so the net is remaining the same. Okay, so that is just this last slide. Maybe we don't need to go into too much detail. Actually, it is just an extension of the detection scheme that we have seen earlier for the SSK. In SSK, I was getting y is equal to h times 1 bar plus n. Instead of that, now I'm getting h times s bar. And the only difference between s bar and 1 bar is that in s bar, at the location of non-zero element, it will not be always 1. It will be actual QPSK or QAM symbol, Emery PSK or Emery QAM or any other type of conventional symbol. But the detection mechanism can be similar. This is actually known as the match filter detector, where I just multiply y with Hermitian transpose of h. Again, assuming orthonormal columns of h, I get s bar plus u. And then I take, now I can't take the real component of s hat, because s bar will have both real and imaginary elements. So typically I will need to take magnitude squared of s hat, and with NT different antennas, what will be the size of this s hat? This s hat will be a scalar or a vector?
Vector.
It will be a vector. It will be an NT cross 1 vector, right? It will be NT cross 1 vector. Basically, individual element of s hat tells me, in absence of noise, this s hat is going to look exactly like this one vector. It will be an NT cross 1 vector with all the elements of that vector will be 0 except the element except the element corresponding to the activated antenna. And so that is how I will be able to detect which antenna was selected, and on that antenna, what was the symbol that was transmitted. Okay, let us not get into this probability of error part. So that is the end of today's lecture content. Let me now show you one paper that Bipin has studied, where this concept of spatial modulation has been extended. So, you know, anytime some new idea comes up and that idea gathers steam and a lot of people are interested in it, obviously a lot of people will start working on it. Then a group of researchers came up with this enhanced version of spatial modulation. By the way, are you able to see the screen?
Yes, sir.
So this paper came in 2015 edition of IEEE Transactions on Communication. It's called Enhanced Spatial Modulation. So you see, this is the same formulation that we had. H is NR cross centimetrics and so on. This is the spatial multiplexing MIMO that we have talked about, where on each of the antennas, a symbol can be transmitted. And so that is different from the space modulation, where we allow only one antenna to have transmission, all others are zeros. And so the transmitted symbol vector can be one of only this many possibilities, total of NT possibilities. Now I will put this paper on our Google Classroom. What I want you to understand is that this idea of enhancing the SM says that what if I have two antennas at the transmitter, transmit antenna 1 and transmit antenna 2. And in the conventional SM, I'm selecting only one antenna. If I select first antenna, then I'll put one of the 4 QPSK symbols on TX1. Whereas if I select second antenna, I will put one of 4 QPSK symbols on TX2. So in the conventional SM, I will have only those first 2 rows. A quick question, what will be the BPCU in this case? One BPCU? I mean, even if I don't do SM, if I have just one transmit antennas, or only one transmit antenna, I will have 2 BPCU because I am using QPSK. QPSK allows me to transmit 2 bits every time I use the channel. In the conventional SM, where only the first 2 rows, C1 and C2 are present, what will be the bits per channel use? We already talked about it. What is the total bits per channel use when we use SM?
Log 2NT plus log 2M.
Correct. So now what will be the answer here? Log 2M for QPSK is 2.
2 plus 1 transmitted.
2 plus 1. So total of 3. I will have 3 bits per channel use. What these authors are saying is that with the same 2 antennas, I can get 4 bits per channel use. How do I get 4 bits per channel use? They are saying that, yes, fine, we will activate one antenna at a time in only 2 out of 4 possibilities. For the other two possibilities here, these rows C3 and C4, we are not going to tie our hands and say that we cannot activate more than one antenna. Actually, we'll activate both the antennas at the same time. But one thing that we will do different is, in case of C3, I will have BPSK symbols that look like this vertical arrangement. This blue X's are the conventional QPSK symbols, these two. This BPSK0 is this green squares. See, there are only two green squares. And BPSK1 is this red squares. And so now I'm able to separate C3 from C4 and C3 and C4 from C1 and C2 also. And so now I have, my transmitter has total of 4 possibilities out of which to select, in addition to QPSK or BPSK transmissions. And so effectively, I will be getting 4 bits per channel use. Okay, so that is the idea. Now, the best way to understand this idea is to draw a diagram like what we have done here. Actually, this scheme will probably work because they are considering only 2 antennas. So you need to draw 2 orthogonal dimensions. In their scheme, for QPSK symbol, they are activating only 1 antenna at a time. And for other 2 possibilities, C3 and C4, they are activating both the antennas. So maybe this I will give you as kind of your self-study exercise. And what I would like you to do is, first of all, draw a diagram similar to this for a case where if they did just the regular SM with 2 antennas, so just first 2 rows, C1 and C2. That will be simple enough. Actually, I've already shown that to you. That you will have to draw 4 QPSK symbols on one horizontal axis, 4 on the vertical axis corresponding to TX2. But then somehow you will have to squeeze in the rows C3 and C4. What they have done here is sort of like that, except here the antenna is not shown at all. This is purely the in-phase and quadrature component of the symbol transmission that happens. But in reality, there are this number of symbols is getting transmitted over 2 antennas, and so we have to actually make use of the additional antenna dimension also. So this will be, I think, a very good exercise for you to do. It will bring you back to our digital communication course, CT516, where what we have studied in CT516 is all the different constellation diagrams, QPSK, 8PSK, 16-QAM, 32-QAM, etc. And I know that you all are very much familiar with that. This is an advanced design of constellation diagram. And this paper already gives you the way they have done this advanced design, but it doesn't, I mean, like many of such papers, they don't give the last level of detail. So they have described their idea, and using this description, they are asking us to figure out the details. And so it is that detail that I am asking you to fill in. Draw a complete diagram for this scheme shown in table 1 and tell me how they are getting 4 BPCU. Okay, so that is all for today. I will conclude today's lecture here, and then we'll meet next Monday, and that time we will actually take up, we'll continue with the topic of the beamforming that we were looking at. But this time I think our focus will be more on the specific algorithms of beamforming rather than just DOA or FOA estimation. And what we will try to do then is kind of use that as a jumping board to get into non-orthogonal multiple access schemes. So we'll be concluding beamforming topic pretty soon, and we will get into the next topic, which is NOMA. This space modulation is kind of an in-between topic that I have sandwiched between this beamforming topic and NOMA topic, with the main objective of giving you this lab 3 that I have posted recently. And then actually this project will be kind of a continuation of this lab 3. If you do a good job in lab 3, then project will actually become very simple. There won't be much to do in project. We'll have to kind of redo the same type of simulations. But the statement of the project is going to be entirely research focused, where you will be looking at the potential application of this space modulation or space shift keying to line of sight channels or Rician fading channels, where the type of channel formulations that we did in the context of uniform linear array, they can be leveraged. And so you will be able to kind of merge the topic of direction of arrival estimation that you will be doing in lab 3 with the topic of space modulation that we have seen now.